Now, let's try to solve this particular numerical question. The total number of claims N on a portfolio of insurance policies has a Poisson distribution with a mean lambda. Okay. Individual claim amounts are independent of N and each other and follow a distribution X with a mean mu variance sigma squared. Okay. So first of all, the total number of claims is following a Poisson distribution, but individual claim amount, the distribution is not given explicitly. A distribution X which is having a mean of mu and variance of sigma square. So the total aggregated claims is this much. So basically it is like S is going with x1 plus x2 plus so on up to xn. Random variable S therefore has a compound Poisson because the number of policies, number of claims is following a Poisson distribution. So S is following a compound Poisson. Derive an expression for moment generating function of S. Okay, so we know by definition moment generating function of S is nothing but the expected value of e to the power of Ts. This we will write it as the expected value of e to the power of Ts given n. We can write that. Now this e to the power of Ts, I will express it as e to the power of expected value of e to the power of T times S. I will write it as x1 plus x2 plus so on xn given n. Now I can write each one individually. Expected value of e to the power of Tx1 given n multiplied by expected value of e to the power of Tx2 given n, so on. So basically now each one is separate. This is a moment generating function associated with x1, x2. But all of them, we said, they are independent and identically distributed. So I can very well write it as expected value of each one separately. So e to the power of Tx e multiplied by e to the power of Tx and so on. So e to the power of Tx to the power n. Now expected value of e to the power of Tx is nothing but mx. So I can very well write it as mx of t, moment generating function of x to the power n. Now this I'll write it in the logarithmic form. mx of t to the power n is nothing but e to the power of log n log mx of t to the mx of t. Now this is nothing but going with that exponential logic. This is nothing but mx of t to the power n. So this is coming out expected value of e to the power of n log mx of t. Now this, if you take it out, n if I am so this I can very well, if you see the moment generating function s of t is e to the power of ts. So similarly this I can write it as mn, right? If I am looking at instead of s I am looking at n, so this becomes mn, and instead of t I am looking at the remaining stuff. So instead of saying mn of t, it is becoming mn log mx of t. So n is nothing but the number of claims. So the number of claims, I know it's a Poisson distribution, and because it's a Poisson distribution, its moment generating function is e power lambda e power t minus 1. So I'll use that. So the t for me is this one. So this will become e to the power of lambda E power t is e power log mx of t. E power log mx of t minus 1. Now if I expand, e power log mx of t is nothing but mx of t. So this is becoming e power lambda mx of t minus 1. So moment generating function of s in terms of moment generating function of x, it has come out. So basically it has come out now, ms of t is nothing but e power lambda mx of t minus 1. Okay, so this part is taken care of. Derive the expression for mean and variance of S. Okay, mean of S, how do you find out? M dash of S of 0. From the moment generating function, M dash S of 0 is what is the mean? So I'll find out M dash S of 0. So first let me find M dash S of t, which will come out as, so this is nothing but M of S, Ms of t. So m dash is the derivative of this, so this will still be ms of t times the derivative of the numerator with respect to t, which will become lambda times m dash x of t. So now substitute m dash s of 0. So which becomes ms of 0 lambda m dash x of 0. Right, m dash x of 0 is nothing but mean of x. I know that mean of x is mu. This is lambda. ms of 0. ms is nothing but e to the power of, ms of t is expected value of e to the power of ts. So t I put 0, e to the power of 0 expected value is 1. So this becomes m dash s of 0 will become lambda mu. So lambda mu is nothing but the mean of your distribution. So the mean of S I have found out as lambda mu. Similarly, now I can try expected value of S squared. The second moment again becomes m dash s, m double dash s of 0. Right, m double dash s of 0. The same logic I will follow. So I know that now m dash of s I have already computed. This is my m dash s. So now I will find m double dash s of t. So which will come out as ms of t. Lambda I will take it out. ms of t. Now this will become m double dash x of t plus m dash x of t times m dash s of t. Now m dash s of t, if I am doing this, again I have to bring this m dash s of t times lambda m dash x of t. Now this is, now wherever required, if I put zeros, right, ms of 0 is 1, m double dash x of 0, m double dash x of 0 is nothing but the variance, expected value of x squared. So which is nothing but expected value, so variance of x is nothing but expected value of x squared minus expected value of x whole square. So expected value of x square will become variance of x plus expected value of x whole square. Variance of x, we got it as sigma squared plus mu squared. So this becomes sigma squared plus mu squared. Now what about this? ms of m dash x of 0. M dash x of 0 is nothing but the mean. So I'll have it as mu. M dash s of t. M dash s of 0, we got it as lambda mu. Right? I got this as lambda mu. M dash. So this is what is working out. So overall this is coming as lambda sigma squared plus lambda mu squared plus lambda squared mu squared. So this is coming out as expected value of x squared. So now I can, expected value of s squared. Now I can very well find out variance of s, which is nothing but expected value of s squared minus expected value of s whole squared, lambda squared mu squared. This and this going off. So this is working out simply as lambda times mu squared plus sigma squared. So this is the variance formula that is coming out for the variance. And so now I have the formulas, right? I have the formulas associated with the expected value of s, which is coming out as lambda mu, variance of s, which is coming out as lambda times mu squared plus sigma squared, right? All right. Now, for a particular type of a policy, individual losses are exponentially distributed with a mean of 100. For losses above 200, insurer incurs an additional expense of 50 per claim. Find the mean variance of S for a portfolio of such policies. Lambda is given 500. Okay, so basically there are some which are below 200 and there are some which are above. So I really need to find out the expected, the total expected losses. And similarly, because the losses are, so expected total claim is what I really want to find out, because even the expenses I have to add. So up to 200 it's only 100, but above 200 another 50 is incurred. So basically I could have written it like the integration between 0 to 200. Now what is lambda e power minus lambda t? Mean is 100. 1 by lambda is 100. So lambda is 1 by 100.01. So this becomes lambda e power minus lambda t, and this has to be multiplied with, I am finding out the mean, so I am actually using a. Similarly, I can talk about 200. It is nothing but x plus 50 times whatever 0.01 e to the power of minus 0.01 x dx. So I could very well use this as 0 to infinite x 0.01 e to the power of minus 0.01 x dx plus 200 to infinite 50 times 0.01 e to the power of minus 0.01 x dx. Now this is nothing but the expected value of x. So which is 100. 100 plus, so 50 times the probability that x is greater than 200. So I could very well write it as 50 times e power minus lambda x. So it is becoming e to the power of minus 200 times 0.01. So which from here I can very well find out, right? e to the power of minus 200 times 0.01. So 50 times e to the power of minus 200 times 0.01, around 6.76. So the mean is the total expense is coming out to 106.76. Similarly, I should be able to find out the variance in the same way, because I can find out the expected value of x squared in the same manner. I find out the value of expected value of x squared, and from there I should be able to find out the variance of x squared, variance of x. So here the x is not just the claim, but claim plus an additional expense. So I got the expected value of x, I got the variance of x. But now we are asking for variance of S and mean of S. Now for this I will use the formulas that I have generated here. Lambda times mu. Mu is nothing but the expected value of x. So we got this as this much. So probably if I want the expected value of S, it is nothing but 106.766 times 500. Similarly, the variance of S, if I want, we got it as lambda times mu squared plus sigma squared. So sigma squared is the one that we will get it through the variance of x computation. Mu squared we have already got it. So based on that substitution, we are going to get the mean and variance both of S. So a step-by-step procedure is going to help us out in solving these kind of questions comfortably. Alright.